Hi, greetings once again, everyone. This is Trigonometry for Students and Surveyors, and the lesson number 22. And we'll continue on. We started horizontal curves. The very first lesson was lesson 21. We stayed internally on the curve. We didn't go out here to where the roads are. We're going to do that today, as I promised. So we'll get started on that. What you're usually given on now, for civil engineering and surveying, engineering stuff, you're usually given, you got to be given some things to get started, not just a blank piece of paper. And you're usually given azimuth and a radius to get you started, and then you're going to have chords. If you're just doing the math for the curves, you don't need the chords. The coordinates, you need a starting coordinate at an intersection point or at a road point, but we're gonna use the chords, but we're gonna not talk about them until the end. We're just gonna solve the main components of the curve here. So we did all this internal stuff yesterday. We found out the mid-ordinate, the angles, but we didn't do the external lengths. We'll get to that. We didn't come in off the road here so much, so we'll get all that handled today, and let's get started on that. So the first thing you're doing is we're given the azimuth and the radius. Our radius is going to be 65 feet or whatever you want to use, whatever centimeters, meters, anything you want to use on that. Just like I say, keep it consistent. And we're given some road azimuths. We have an azimuth here of 38 degrees. That'd be north 38 east, or just 38 degrees on the azimuth. And on this one here, our azimuth is 323 degrees. So we've made an intersection. Now we have our PI, our point of intersection, where these two roads meet. That's the point of intersection. Okay, that's where that is. Now on civil engineering, you got to have a starting place, because these bearings could be miles apart, or they could come together. So you need a coordinate to start with, but we're gonna we'll back into that. We won't do that just yet. So we'll just assume we have a coordinate up here. We'll start with a coordinate up here. We won't even start with a coordinate. We'll just start with this up here. So now we need to find. So what you want to do is you need to find the angle here. What's this central angle? We call it a delta angle. And all you're given so far is a radius and these two bearings. Well, that delta angle is going to always be the same thing as your what's called a deflection angle. And a deflection angle would be, say you're sitting here, if you're using a scope or whatever, or you're just doing your calculation, it's deflection angle. You have these two angles. You flop a 180 over there, and so you're looking this way now. You're looking on the straight projection of this bearing, and now you're coming down and you're arcing to this bearing here. And so what that is you have a 38 degrees and 143 degrees. So you subtract 143 from 38, or vice versa. If you do that, you're going to get a negative number. Just take the negative off. So 143 minus 38 is 105 degrees, and that is your deflection angle. So that ends up becoming your central angle on your curve, and that ensures that curve is right angles, or the radius point is right angles to this road center line, or this line that you're drawing on a paper, whatever this line is going to be. So these are all right angles. That's what you call a tangent curve. It's going from a tangent, a straight line, into a curve, and it goes around a right angle with a radius point. So that's how you do that. And you'll notice that this is a 180. A straight line is a 180. So if you have 105 degrees on this deflection angle, whatever's left over minus 180 is going to be 75 degrees. All right, so we have that. Now we're going to rate the radius again. We did that on the last introduction to the horizontal curves. We'll do that again. You have a radius of 65, which is half a circle, and we know that the circumference is the diameter of a circle times pi. So we got that again, so we'll have that. deflection angle. Circumference is radius times 2 times pi. So our circumference is going to be 408.4070, and then that's our circumference. Now we have our delta angle and we have our circumference. So now we're going to find the curve length. This is what we did yesterday, or the last lesson, lesson 21. So 360 is a full circle. What are we trying to do here? So our circumference is the full circle. We want 105 degrees divided by 360 degrees. That's the portion of it. That's the delta portion of the full 360 degree circle. That's the delta portion of it. That's the central angle of that. So you divide those, you come up as 0.2917. You multiply that times the circumference, and then this is your curve length, 119.1187. So we're moving right along here. We got our angle from the two bearings. We got a deflection angle from two bearings. That translates to our central angle. We now have the curve length solved. And now, what are we going to do here? Delta. Now we're going to use a pi. Okay, so now what we need to do, we've got a radius. We've got a radius. We got to find where this is at now. We might have done this angle backwards. Maybe we should have found the PC first, but it'll all work out. You got to go back and figure out what this length is from the PC to the PI. They're going to be the same on both sides because it's an even length curve. So what you do there is you go half delta. It's half delta tangent. The tangent length. This is called the tangent length right here. Let's see, I thought I had it written in once. TA tangent length. Well, you get the idea. Tangent length is 1/2 delta, so that's 52.5. Half of 105 is 52.5. You take the tangent of that and then multiply it times the radius. And that gives you 84.7096. Now, you measure back from this PI that length, and then that's where or whatever calculations you happen to be working with. But that's the formula to find your PC. And then that curve will fit in here perfect. And then you can do the same thing for your PT, the same distance from here. Now, what I talk about in coordinates is in surveying, you would start out with, or engineering, you'd start out with a coordinate on where your last bearing was going to come from. So your bearing is 38 degrees. This might be a curve, this might be another straight. Like over here we have a curve and then it goes straight. So you have to have a coordinate where you're going to start. So we have coordinates here, we have coordinates here, and from these two coordinates and those two bearings, we end up with a coordinate for the PI. So we have this coordinate we measure back from there on that same reverse bearing, which is 218. So that's a 180 to that 38, 180 is 218. And then that's where your PC comes from. That's the point of curve, midpoint of curve. And then this is your PT, your point of tangency, a point of tangent. Then you're going straight again to your next PC, point of curve, and on you go and so on. Roads are a succession of those, a sequence of those types of things. All right, so we have that. So now we know where to put the PC to make that curve fit those two road center lines. Use PI chord and tangent to find the PC and P and the radius point. Now that we found these, we're going to find the radius point. Now remember, this is a tangent curve, so it's a right angle. That's why we have our two square boxes. Whenever you have a right angle, you can put in a square. That makes sure that they know that it's a right angle. It's a 90-degree angle. So we're going here, and we need to find this point here. So we're going back. We can go back this way, or we can go up 38 degrees, or 38 degrees, and then go 90. 90 from that is 128 degrees. So if we went 120, we have a point here, and we go 128 degrees, that's going to give us our radius. The other way to do that, 38 plus 90 equals 128 degrees. Or you can go, if you're going this direction, you can do the same thing when you get to your point. When you get to that point, 84 feet, then you hit a 270, which is a 270 degrees off there. And that's going to give you 218 plus 270. Well, that's over 360 degrees. So you subtract 360 and you end up with 128 again. So there you go. Now, where did this come from? The 308 going that way. Well, that came from 128 plus 180. That gives you your back bearing. Now, those are all kind of skipping through this a little bit. Those are all in the previous lessons. All that's, we saturated that with, inundated that with the previous lessons. So I don't want to keep repeating myself. And this is the same thing here. You're going to go up 323 or down 143 degrees. You're going to go down from this point on this bearing, on this line, on this azimuth, 84.7096. That's your PT point. Then you want to do a right angle from there. So you want to go a 90 degrees plus that. And that's going to give you 233 degrees to the southwest. And the back bearing of that is 53 degrees. And again, you could go up from this bearing. You could go to 270 plus 323, and again subtract from 360 and you'll get 233, and your back bearing is 53. Now you add those two together, so now you have those bearings. You have 308. Let's see, what do we have? We have 308 that way, and so to get this, the other way to get these angles. Now we're confirming these angles. We have 105 degrees here, so that's where we came up with this angle. If you're using your bearings, we can confirm that now by using these to make sure, to ensure that we're absolutely right angles, because we turned a 90 degree here and a 90 degree from this point here. So what do we have? We have 308 degrees minus 360, and that gives us 52 degrees. And over here we have 53 degrees. So we've added those together and we get 105 degrees. So 308 going that way, we got 300, this is a degree, 360 degrees minus 308 gives us 52 degrees. And then over here we have 53 degrees, right here, 53 degrees. So you add those together and you get 105. The other way is to take this bigger angle and take that. And you go 308 degrees minus 53 degrees minus 360 degrees, and you get 105 degrees again. So we've confirmed it 3 ways now. And all this is done. This is just a backwards way of doing it. Another way, just another way of doing it. It's good to have many different ways to check yourself. So where are we now? Okay. PI coordinates to find the PC, the PT in there. So now we found the radius point. Okay, now what we didn't have on the other one, we solved the mid-ordinate, and we'll do that again here in a minute, but we didn't have what's called the external length. That's the difference between this mid-ordinate point on the circle. This is the mid-ordinate distance. Mid-ordinate distance is where the apex of the curve meets the halfway point, the mid half delta on there. This is the distance. So we want this distance here. Well, it's just again, we have a triangle here. We have a right angle triangle. So use PI coordinate tangent to find the PC. Use 52.5, 1x, the cosine of that. That's the cosine. That's the sine. To find the long hypotenuse, that's 106.7742. Yeah, 106.7742. Again, that's right angle triangles. We've done a lot of that, so I'm not going to belabor that any more than I have to. And then you can do the same thing with the sine of that. So the cosine of that was of course the 6 times 65 times the radius, times 65 to find the hypotenuse. The sine of that is this one over here, 84.7096 is 52.5. The sine, inverse that, 84.7096 times to get that full length of that hypotenuse of the big triangle. Now you have a radius of 65 feet. So subtract the radius from the full length, and now you have your external length of 41.7742. That's your external length. Okay, now the mid-ordinate, we solved that the other day. First of all, let's do our, we didn't do our, yeah, let's do the mid-ordinate first. The mid-ordinate, again, you have a right triangle here, as you can see, 52.5. That's the decimal. It's 5230 ball, 3000. Okay, and that's just survey talk. 39. So you have that length. We're trying to find that length. So you just want the hypotenuse. You just want the tangent. No, we don't have this yet. We want the tangent of. Or do we have this yet? I don't think we've solved. We haven't solved the chord yet. Let's stop and solve the chord yet. The chord is 1/2, 52.5. We have a radius, and now we want the sine of that. That's the hypotenuse. That's the opposite over the hypotenuse. We want the sine of that. So I'll just do it real quick here, just to make sure I'm not flubbing up. So we want 52.5. The sine of that, 65 times is 51.5680. There's your half distance. Double that, and you have your chord length, your long chord. That's called the long chord. And that's your half chord. And of course, the other way I showed you yesterday, you can go the law of cosines, a squared plus b squared minus 2 times a times b times the cosine of the angle. Subtract that square root, and you're going to get that same 103.3599. So 103.1359. That's your long chord length. So we want this one here, so 52.5. Now that we have this, we can either use the tangent. So 52.5 tangent. We're going to 1x that because we're over 45 degrees. We're going to 1x that. And we're going to go 51.5680 times 39.5695. The other way to do that is cosine. So let's go 52.5. Cosine is 0.6088. Now we're going to go 65 times 39.5695. So that's this length. And now you have, well, now we know that this is the, I don't know what that length is. They call that Q. They don't really call that a length, what that length is. But they do want, this is an important one, mid-ordinate, the mid-ordinate, middle ordinate length from here to here. So you have 65, we have 39.56, so 65 is your radius. That's 65, anywhere on that thing is 65 from here. And then minus 25.4305, that's your mid-ordinate length. Okay, so we've taken just that little bit of half, and we built all this already. We've confirmed that, we've got that in there. We use that to confirm the angles by using the bearings and the distance there, we got that. What are we asked to subtract? Okay, I've already done that. Subtract that length from the hypotenuse, from the radius to get the external length. We did that. Cosine for adjacent, we got that. We just did that. Middle order, we got that. Add the tangent length and curve lengths. Okay, now we're going to get what's called stationing. So we have these on surveying and engineering. They call it station. They're just distances. It's just they write them a little different. Stations are like 100-foot stations, and their fractions are their partials, parts of stations. So we're pretending that there's a road coming through here called Road A, and then this is going to be a new road into our new plat, and that's going to be Road B. And of course, this is another road. The road's coming into the plat or into the subdivision or country road, whatever you want, is coming back out, and it's continuing on, and it's going to have a length to it. So we're starting out. This is a monument. Let's just call that a monument. That's called an intersection monument. Then as far as the station's going, this is an equation station. So 2104 or 2104 plus 95.457 that way. That means it started way down here somewhere. Equals 10 plus 90, 00 going that way. Okay, so now we've added 38 feet to that, and we have 11 plus 46. So let's just 10, 90, enter, 38 plus, we have, oh, that's degrees. Sorry about that. 10, 90, enter, 46 plus, I did it again, 1090, enter, 56 plus. So now we're at the PC station is 111 plus 46.00. That's where we're at there. So now we have the station there. We don't really need the station there. We can add that, but that's a PI. We're really looking at the curve length. So we have 11 plus 46 at the PC. Now we have our curve length at 119.1187. So 119.1187 plus 12 plus 6512. That's the station. That's the road station here at the PT. And then you just keep going and following it all around. We would have 39 feet here. Let's just go 39 plus. The station here at the PC, the point of curve is 13 plus 0412. All right, so there's your stationing. That's how you do that. And we're going to go to radius add. Okay, so we got our station. So we've done all these already. What is the tricky part is maybe you're only given 2 coordinates to start with. That's all you got. 2 coordinates. You got this coordinate here, this intersection, and you got this coordinate here at the PC. So now you got to figure it all out from there, but they're going to give you the bearing, just the bearings. You have 2 coordinates and the bearings, and so that you're going to have to find all this yourself. So that's called, the data collectors do them, or we'll figure out how to do them here. We're not going to figure out how to do it here. That's all back in our oblique triangles. But I'll just go through the process with you. First thing you want to do is you want to inverse these. You have coordinates here. So we have a coordinate here, 5,000, 5,000, make it simple. This is at 1. That's 1. Now, you don't have a coordinate here. Oh, yes, we do. We have a coordinate here. So you have to inverse those coordinates. And then this is the difference in the northing. This is the difference in the easting. Latitude and departure, I have them stored. And then that's just a right angle triangle. Then you get the arctangent, you divide them, divide the departure from the latitude. Let me see if I have those stored. Recall 5, yes I do. Recall 4, yes I do. Okay, so we're gonna go departure, recall 5, enter, recall 4, divide. I got 13 now. I want 13.3335. I want the arctangent of that. That's 85.7109. So that's the decimal azimuth. If you want to convert it to hours, minutes, seconds, or degrees, minutes, seconds, you have your conversion key on these, and on the free 42, they're in there. And on a few lessons, I showed you how to convert back and forth longhand. So you've got that. Now you got your bearing. You got your azimuth, your bearing. And then a squared plus b squared gives you the distance. A squared, b squared, c squared, 161.5322. So now you have all that. So your bearing's right there. Your back bearing is 265,701. Now remember, we weren't given any length. We were just given the azimuth and what they want the radius to be. They want this to be a 65 foot for the road width. Come back in 30 feet or so, or 25 feet for the curbs, the curbs. So this is going to be the center of the road. You're going to have your road, center line of the road here. You'll have the same distance out there. You'll have a curb, the face of curb will come around in here. So that's what they want. That's what they engineered. Now you got to find out how that fits on the ground. So now you have, so you're starting out with this distance and that angle, and you're given these two azimuth, 323 and 38. So now you just got to subtract, or you got to find out your angle here. So you have a 323 there, and your back bearing would be 265. So let's just run that real quick. 323, enter. 265.7109 minus is 5728.91. So that's your angle here. So you do the same thing over here. You have 38 degrees there, and you have, what's our bearing here? 85. So 85.7109. Enter. 38 minus 47.7109. I didn't get that. Let me try that again. 85.7109. Probably didn't hit a key hard enough. Enter. And 38. 47.7109. This time it worked. They don't always put out the right answers if you don't give them the right input. So there you have that angle now. So now we can go into our oblique triangles, go back into there, and we have, I'm not sure now right now if it's law of sines, cosines, but we have one distance and two angles. Since we have two angles, we know that we have a third angle here, because they all got to add up to 180. So we know we have everything. So we have three angles and one distance. So from that, we can solve, I'm not going to do that right now. That's complicated enough in itself in another, in past lessons. But you can go back and find out oblique triangles, and I think I just did it. Maybe just yesterday. On yesterday's, I don't think I did. But anyways, you can go back to the oblique triangles and figure out just exactly which function to use, law of sines, law of cosines. And anyway, so there you go. So now you have your angle, you have this one distance. So you'll be able to solve this distance. You already got the bearing. You'll be able to solve this distance and then this distance here. And then once you have that, now you know you got a 65-foot radius. You'll come back from that coordinate and come back. And you'll come back on this same bearing, the back bearing, 218, that distance, and that's going to be your PC. Same with here. You can go back that way, and there you are. So we came up here. We have this. This is 5,000, 5,000, 5,000. We created this one by putting in that bearing and that distance, or by inversing, and then putting in the bearing and that distance, and that gave us that coordinate. So now we started out with this coordinate. Now we have this coordinate. Then we have this bearing. All right, so now we are going to go up on 38 degrees. We are going to go up 56 feet. That's kind of just a number I threw in there. And add it to that northing and easting, and that goes back into our coordinates, which I'm going to say lesson 5 or 6, we started carrying coordinates and traversing like that. Go back there and you can see how we did that. Very straightforward. So it's right there. So there's a coordinate for that one. Now from there, we can go up to here, or we already started from here, but we can confirm that. One way to double check that too is go from here to here, enter these. I like to enter these into my data collector at specific things, 7 and 3, Northing is usually my 7, easting is 3. And then you just store plus, and it adds to it. Then you can do the whole length of it. You could add 56 plus 84,7096 together. Start from this 5,000, 5,000, go up that degree, that combined length, and that'll give you that one there. And then so on. And then you can come down from this coordinate here, come down this bearing here, 128 at 65 feet, and you're going to do it with the northing, and then do it with the easting, and you'll get those. I just blobbed them out, and you'll get those coordinates there. So let's see, I can do that one for you. I'd have to enter those in there. So one way to do that is just to go 128 cosine is the northing, and I want it 65 times, it's a negative 40.0180. Now I'll just add it to that one, 5044.1286 plus 5004.1106. That's what I blobbed out. These whiteboards are very sensitive when you put your hands on them. They smear pretty easy. So that's how you do that. Now we're going to do the easting. We'll go 128 degrees. And now we're going to use the sine. That's for the easting. And we'll go 65 times. That's 512207. We'll add that to that easting. 5034.4770 plus 50856977. And that's what you use. So now we have that in there. So if you want, we could go up there to check this one. We'll go 53 cosine. Our radius is 65 times 39.1180. We'll add it to 5004.1106 plus 50432, 5043.2286. That's how you do that. And we'll do the same thing here. 53, the sine, that's the easting. 65 is the radius, times, that's 519113. And we'll add that to 5085.6977 and plus 51376090. Just so you know, I'm not bullying you, okay? And that's what you can do. You can go all the way around up to there. That's how you get that. And go down there to get that. So what I would like to do is I generally store these. As I calculate one of these, I'll store that and overwrite it with my next calculation and just keep adding, and then maybe do a check back to it. I think we've covered it. So that's your horizontal curve. We've solved the chord length, the curve length. We've got our central angle, which we call the delta angle. This is my symbol for angle. Where did I have it here? I got it all over the place. Right here. That's how we write on the stake. We call it an angle point. We just put that in there. The funny thing is, some of the new contractors, they don't know what that means. They'll ask you, what is that? What is that symbol? And traditionally, it's been very well known. So yeah, we have all our stationings here. That's going to do it, I think, for this lesson. I had to lay this out. I think we went through everything. Okay, that will do it for the lesson, the second lesson in horizontal curves. We'll see about what I do next on that, and thank you for take a snapshot of this, take a screenshot of this, and please like and subscribe to my channel, and I hope it helps you get your licenses or helps you be a better surveyor or a better student. Hope it's a real practical application of trigonometry. If you're a student, at least you see how it works and how we use it in the engineering and surveying field. So thank you very much, and see you for lesson 23.